Okay, so this question is once again looking for a ability to spot carbocations and carbocation mediated processes. So here, if we have an alkyl bromide and we treat it with water and heat, and I think when I've used this in an exam, I've also said that the product has a molecular formula of C9H12O. Okay, just to give a little bit more push in the right direction towards the product. So C9H12O, if we look at our starting material, we've got 6, 7, 8, 9 carbons. We've got 5 protons or hydrogens around the benzene ring. Then we've got 2 here, 1 there, so that's 5, 7, 8 plus 3 is 11. So we've got H11 and then Br, so no oxygens. Now, in going from this to that, we must be adding an oxygen somehow and 1 extra hydrogen overall. And so, we've added plus OH and lost Br. So I don't think it's too much of a stretch to think that we've replaced the bromine in the starting molecule with an OH group. Okay, so what are we going to do? Hopefully, we might recognize that with heat in this molecule, we can go through via a carbocation. Okay, so if we heat this molecule, we can get loss of the leaving group to give us a carbocation, and that will be a secondary carbocation. Okay, now that secondary carbocation could recombine with the bromine that we've just kicked out. So we're going to lose bromide here. However, the trick to this question is spotting that a secondary carbocation is not very stable and that this can rearrange to a more stable carbocation. Now, often in carbocation rearrangements, we focus on the stability between tertiary carbocations being more stable than secondary, than primary, and methyl being pretty terrible. However, carbocations can also be stabilized through conjugation or resonance. Okay, so if we can put the positive charge next to an aromatic ring or a double bond, we can draw other resonance forms for that carbocation that make it more stable. So now the trick to this question is to recognize that there are hydrogens next to this carbocation, and that if one of those migrates with its pair of electrons, we're going to get a new, much more stable carbocation. So we draw out that product. I'll draw in the proton or the hydrogen that didn't migrate, and I'll draw in the one that did migrate. And just remember that there is another hydrogen in that position that I haven't drawn in. Okay, it's not that there's just 3 substituents, there's an extra hydrogen there as well. So now, why is that so stable? It's what we call a benzylic carbocation. And it's stable because we can draw other resonance forms for it. So, for example, we use these double-headed arrows for resonance structures. I'll do this in a different color. So I can draw this pair of electrons going out there, and we're putting the positive charge onto the benzene ring now. Okay, so these 2 pi bonds are unchanged. However, we've lost a bond from that carbon, and it's moved across to this position here. Actually, I'm going to stop drawing that hydrogen there because it's no longer really useful to remember that it's there. So we've drawn one resonance form, but we can draw others. So I'll stop using colors now. We can draw that bond there moving, and we end up with that one being there, this one being here. The positive charge is out on that part of the ring. We end up with that. And one more, we can draw a resonance form where this pair of pi electrons can move. And we end up with our fourth resonance form. So all of these contribute to the overall structure of this benzylic carbocation, and they stabilize, and that's why it's so much more stable than the original carbocation, even though they're both secondary. So this is still a secondary carbocation. Okay, so we can now attack that carbocation with a nucleophile at any of the four positions in those resonance forms that have a positive charge. However, the first resonance structure has a positive charge at the carbon outside of the ring, and if we attack that position, we leave a stable benzene ring intact in the final product. Now, I could get the bromide anion to attack that position, and we would get to a benzylic alcohol bromide. However, the product, we're told that it's C9H12O, so it must be an alcohol. So we're heating this reaction mixture in water. So there must be a lot of water, and so by sheer mass of water, we're going to get the major product being the product of water attacking that carbocation. So we're going to attack that, and we're going to get this is the product, and then that is just going to simply lose a proton. We could draw a curly arrow for that if we wanted, but I'm sure that you could. And we're going to get that as the product. Okay, so hopefully that shows you how we don't just have to think about tertiary versus secondary, primary, and methyl in terms of stability of carbocations. We also need to think about resonance effects. And so for this question, recognizing that we're getting alcohol as the product via a carbocation is one half of the question. The second half is recognizing that we're going to get a rearrangement before we get the nucleophile capture the carbocation. And so we're going to get this benzylic carbocation that's captured by water to give this benzylic alcohol. Okay, so hopefully that helps with that style of question. To get full marks for it, you really need to spot that it will rearrange. Part marks might be if you gave a answer in the exam that showed the alcohol capturing this carbocation here to give a different product. Okay, that's it for this question.